Good morning and welcome to the next technical session of the Xendee University Week today. Now we are talking a little bit about small modular reactors, and we have two presentations today. The first one is from Timothy Grunloh. He's a principal research scientist at the University of Illinois in the Department of Nuclear, Plasma and Radiological Engineering and Associate Director of the Illinois Nuclear Power Institute. At the University of Illinois, Tim contributes to multidisciplinary research, particularly at the intersection of computational science and advanced nuclear reactors. Through the Illinois Microreactor Research and Development Center, Tim's work is also focused on enabling and expanding safe, peaceful use of nuclear power. Current research activities in this center include microreactor modeling, and I think this is what we are talking today, and simulation, siting analysis, market analysis, instrumentation, operation, reactor control, licensing, and policy. The center's flagship project is the ongoing collaboration with Nano Nuclear Energy to deploy a Grunloh modular reactor on the university campus as a research reactor. Prior to the University of Illinois, Tim worked in the advanced reactor design industry. Thanks, Tim, for taking the time to talk about your research and your work, and the floor is yours.
Great. Thanks. Thanks, Michael, for that introduction. Appreciate it. Looking forward to chatting. Yeah, so as Michael mentioned, I'm Tim Grunloh here at the University of Illinois. And in this talk, I'm going to talk about how we see the next 5 to 10 years of nuclear, and how our research is designed to support that, and what we're targeting and why. So yeah, that's the baseline. So in general, there's a lot of new excitement around nuclear. There's a lot of things driving that. Some of that is increasing power demand from AI, as well as other power trends that are kind of coming to a head. There's also a lot of new thinking in how we can design technology. So up until now, the status quo in the United States and in a large part of the world has been very large reactors that power large cities, millions of homes, and use water technology. That's still going to be true to an extent moving forward, but there's a lot of designers looking at different technologies, both in terms of the technology type, which I have here at the bottom from the Gen 4 International Forum. If you follow nuclear, you hear things about like sodium-cooled fast reactors, gas-cooled factory reactors, molten salt reactors, high-temperature gas-cooled reactors, all kinds of different reactors. And then we're also seeing a lot of new thinking around the size of reactors. As we'll talk about a little bit later, some of the assumptions that went into designing gigawatt-scale reactors may or may not be true in the future energy markets. So a lot of folks are looking at much, much smaller reactors. And this is where we find our research at the university. We see that there's going to be a paradigm shift in the way these smaller reactors in particular are deployed and operated. That's going to open up a whole lot of new different things that we can do. And this is the research that we want to do. How can we deploy these reactors for new applications? How can we operate them in new ways? How can we leverage the safety and reliability record of the current fleet in a reasonable way? So at the University of Illinois, we mentioned the microreactor demonstration project. We'll give a status update on that, where we're actually trying to deploy a reactor on campus. And as I speak to you now, I'm about 800 feet from the proposed site that we're working on. We're going to use this reactor, for several purposes that we'll talk about, but one of that is just to show the reactor can be built, that it can be deployed with existing infrastructure. This is part of a larger Illinois Nuclear Power Institute that was just rolled out at the university, which is our larger workforce and R&D hub that's dedicated to solving critical deployment challenges. Here we focus on the next generation of nuclear, but also the current generation and workforce development and that kind of thing. So what's different about smaller reactors? The first thing is that they're smaller, as you might guess. And so if we look at the potential site footprint, this is from an EPRI report on the left side. The status quo reactors right now are on hundreds, if not thousands of acres. It's quite difficult to site. Just siting them can take a couple of years. As we go to smaller reactors, it gets much smaller. So I mentioned that I'm basically sitting next to the site. The site that we're developing here is about an acre. It's next to the building that I'm in. It's next to other buildings. It's next to the energy infrastructure of campus. The other thing that's different is the technologies. So on the right, I've drawn a bunch of different potential industries that use energy and the heat of the energy that they use. And on the bottom is different reactor types. So light water reactors, the type that we do now, the process temperatures of those tend to max out around 300 degrees Celsius, give or take. Some liquid metal reactors can go up to 500, 600 C. High temperature gas cooled reactors can go up to 1000 C. And the point of this slide is to show that basically the higher you can drive the temperature, the more markets you can address. So there's more customers that we can approach. So with smaller reactors, we don't necessarily have to compete at grid scale electricity, immediately. We can get down that learning curve a little bit by approaching some of these other markets that are, interested in behind the meter power, that kind of thing. So not just AI, although AI is part of it. Another enabler is just the size. You can if you have an industrial process that you want to run a reactor to power, you don't want to have to accrue 10,000 acres, but instead you can just do an acre, much more realizable. So these are some of the advantages that we're seeing. Other advantages are in the safety. I'll stop short of saying that microreactors and SMRs are safer than the current reactors, because every reactor that we operate in the US has very strict safety standards. But what I will say is that it is easier to make these microreactors safer. And part of that, there's a lot of reasons for that. Some of that is in the fuel. For example, TRISO fuel has a lot of extra barriers in there that I won't go into right now. But some of this is just the size. So one of the major drivers of accidents or consequences in nuclear accidents that you hear about, the big ones, is decay heat. So this is a unique thing about nuclear. When you shut down a coal power plant or a natural gas power plant, there's no more energy being generated. There's some residual heat that needs to be removed. You'll still burn your hand if you touch the boiler. But with a nuclear reactor, you shut that down. There's still that radioactive byproducts from the fission process that do generate heat. Immediately after shutting down, you're looking at about 7% of the energy. With a major gigawatt scale reactor, you're still looking at 180 megawatts, give or take, which is more energy than the University of Illinois uses. So that energy has to be removed with large diesel generators, which, for example, in Fukushima were washed away. So that's quite challenging. With a microreactor, if you're operating at, for example, 67 times lower power, you have 67% decay heat that needs to be removed. So in that case, with our reactor that we're looking at 45 megawatts, within, immediately after shutdown, you're looking at, 2 or 3 megawatts, which the university has several buildings that use that much energy. So it's, it's still a lot of energy for an individual, but it's not that much energy. After a week or so, it gets down to the energy of like a Toyota Corolla, which you can just imagine there's only so much damage you can do with a Toyota Corolla. And so, it's much easier to protect against that. And as I mentioned, there's some other aspects that I won't go into that are a bit more technology specific. And so what does this all come down to? When you say we're shifting the paradigm, what are we thinking? So we have all these different sizes of reactors, technologies. The left is kind of a picture of the status quo. When you look at the levelized cost of nuclear, you see a lot of that is driven by investment cost. And a much smaller part is fuel and O&M. And part of the reason that we saw a significantly stunted rollout of nuclear since the 80s, part of that was public perception. But this plot down in the bottom left shows that part of that was just cost. Reactors got more and more expensive to build pretty majorly, and that was a big reason for the slowdown in nuclear that we saw in the U.S. and in other parts of the world. And this increasing cost was seen, maybe these construction projects are potentially too large. So that's why it motivated a lot of vendors to go to smaller reactors. Now there's no free lunch. As we go to smaller reactors, we end up on the right side where we see, some estimates show that, the capital expenditure becomes a much smaller part. So that's great. The capital project is much lower risk, but we see a lot of the risk getting shifted to operations and maintenance. So, how many people can you operate at the reactor? How often do you need to refuel? What kind of instrumentation you're using? What kind of recalibration? This is where we see the risk. In this particular study, the baseline case showed O&M being very small, but they showed potentially major upside in that cost, major upside risk that could potentially drive the electricity cost. So this brings us to the Illinois Microreactor Demonstration Project. So, again, mentioned we're in the process of licensing a reactor now. The goal of this is to operate this reactor as a research reactor. Now, research reactors are nothing new. There's 30 of them in the U.S. now. There were up to 50 in the heyday. Rich tradition of supporting the commercial industry with with research reactors. What's a bit different than ours is we're going to be focusing on the O&M mission rather than radiation science and that kind of thing. It's going to be more about how do we operate these with recalibrating fewer instruments? How do we take steps towards things like remote operation, autonomous operation? How do we integrate new cybersecurity, that kind of thing that we're looking at? So, the point of this project is, we've got two main objectives, and then there's a cross-cutting objective. So we're a university. Education, training, and engagement is going to be a big part of that. So education, we want to educate our students. Training, we want to train potential operators for the commercial fleet. This will be a new thing that will be available because we're using a commercially representative technology, and train some of the tradespeople that will work on it. And then, public engagement is a big part. In nuclear, all roads go through public engagement. I'll be the first to say our industry has a little bit of a PR rehabilitation that we need to do. And so we welcome, folks to come see the project. A big part of why we're doing this is to show that, we're not putting this in a place that makes it look like we think it's unsafe. I'm putting this near where I live because I believe it's safe, and happy to engage on that. The other core objective is research and development. So this is what we're just talking about. How do we deploy these things? How do we optimize the operations and deployment? How do we develop the critical enabling technologies and developing synergistic applications for that kind of thing? Cross-cutting demonstration is just showing that it can work. In nuclear, there's a large sense that folks are going to line up to be second. So once we show that we can build these things on a schedule and budget that's predictable, a lot of folks are going to be interested. Beyond that, we're tying into Abbott Power Plant, which is the central heating facility on campus that provides district heating for the university as well as some of the electricity. It's an existing infrastructure. So by tying into that, we show that we can co-locate with the energy user, which has not been demonstrated in the US before. So this will be a big enabler of a bunch of different economic applications. So just to tell a little bit about where we're at and the technology. So we're partnering with Nano Nuclear Energy. They're developing a high temperature gas cooled reactor. It's a 45 megawatt thermal unit. It uses TRISO fuel, which is a very small kind of poppy seed size fuel kernel. There'll be many millions of these kernels in our reactor. On the right, you can kind of see how these tiny kernels, which is what we see now, build up the reactor. So even the kernels that you're seeing now, there's several layers of protection. Chief among them is a layer of silicon carbide that is very robust to the conditions you see in a reactor. All the radiation, radioactive fission products stay where they're born. So the fuel's a bit more expensive, but it enables a much more simple safety case that we're seeing. The site that we're looking at, I mentioned, is about an acre. So it's this orange area on the left side of the plot next to Abbott Power Plant, and we'll tie into the steam of Abbott Power Plant. So where are we? This is a timeline that shows the project was kind of born in the 2019 era. It's like observing there's a new generation of nuclear coming. A lot of things are going to be different. How can the university support it? Research reactors are a great way. In 2021, we officially started the project with the regulator by issuing a letter of intent. We got our docket number. Then for the next few years, there's a lot of project development, a lot of regulatory engagement in a pre-application setting. We reached a major milestone in March 31st of this year when we submitted our construction permit application. So we are officially in licensing, deeply engaged with the NRC on an almost daily basis. As of a couple of weeks ago, they officially accepted our application for review. Based on how we think the next reviews are going to go, if everything if we pursue everything aggressively, we're looking at submitting the next phase, our operating license, late 2027, potentially 2028. This puts us on a track to begin low power operations 2029 with a NRC licensed reactor, and we can start fulfilling that research mission. Now, the project itself has given us this sense of boots on the ground mentality. What does an actual reactor project look like? What are some of the constraints that would drive that? And we're using that to perform research now that's being enabled by this project, which we'll talk about now. I assume this group is pretty familiar with microgrids. So there's a lot happening in the microgrid space in general. Some of this is driven by AI. Some of it is just by increasing electrification and all kinds of different integration of renewables, that kind of thing. So as you know, we participate in several different IEEE working groups. How can we do this? How can we look at how smaller nuclear can integrate with the microgrid? As I mentioned, the current status quo with nuclear is fulfilling the major grid. Nuclear is kind of sensitive to the power coming in, that kind of thing. It assumes there's going to be many customers and predictable load, that kind of thing. Smaller reactors, we think, enable much wider operations. So we're looking at things like co-locating power, like cogeneration, virtual power plant, that kind of thing. So there's a wide range of things that we can do. And so, the work that we're doing in the group and INPI now is on optimizing some of these, uncovering what the right licensing strategy is, what the right technology is for your application, how you're going to operate it, that kind of thing. Our university itself is an excellent laboratory. So we have a very well instrumented data energy and ecosystem with data. So we have something like 500 buildings on campus. Hundreds of these are supplied by both steam and electricity from Abbott Power Plant, who again is a university owned and operated power plant that we partner with quite a bit. We have very finely resolved data on all of these buildings for steam needs, electricity needs, and chilled water. And so we use this to construct different models of different systems. So, obviously we can model a campus, but we can model residential areas, office areas, sports complexes, that kind of thing. We also have a very robust energy ecosystem. So we have Abbott Power Plant, which is coal, natural gas, and fuel oil. We have 2 solar farms on campus that produce a total of about 20 megawatts. And we also have a power purchase agreement with a nearby wind farm. We have data on all of this. We use this to kind of imagine different environments. We've done some research with Xendee, with Michael. We took some of this data. We simulated the campus. We simulated dual demands for meeting both the steam needs for the district heating and the electric heating. And we ran out a bunch of different scenarios about what it looks like to integrate nuclear into a campus. We learned a lot in this. We did 8760 data over a representative year. We had, our Blue Water supercomputer involved in that. We'll talk a little bit more about that in a little bit. Learned a lot about how you kind of optimize around 2 different energy streams and that kind of thing. One of the really interesting things that we learned is the value of storage. So we'd always suspected that energy storage is going to be really important. Nuclear is going to be capital intensive. Even the new generation will be very capital intensive compared to things like natural gas. So there was always a suspicion that the energy storage would be good. So we modeled thermal energy storage, which is actually part of our proposed application where we're going to have molten salt energy storage. We noticed that if you incorporate energy storage, at least for the case that we did, you can get about a 20% reduced reactor rating and still meet the power demand throughout the full year. And you can translate this to a 15 to 20% reduction in cost, depending on your cost models. So huge savings there. A lot we learned. Of course, AI is on a lot of folks' minds now, especially in nuclear. So we're also using similar data, similar techniques to look at data centers. So I mentioned we had the Blue Water supercomputer on campus. At the time, this was one of the biggest supercomputers on the planet, at least the publicly known ones. It was about 10 megawatts, which now seems kind of cute. I think they hand out 10 megawatt data centers at expo booths at conferences now. But we use this data. We have real-time data for both the cooling and the energy demand. We're using this to look at things like integrating absorption chillers to get kind of free cooling, that kind of thing. I don't have slides on it here, but we also look at non-data center applications. We do a lot of industrial applications where there's steam needs and electricity needs. There's a lot of value to be made by designing that co-located facility where you're using the steam without having to convert to electricity first, as well as the electricity. You can do things like clean industrial processes, that sort of thing. So as we move away from the co-deployment and into the enabling technologies, I'll move through some of these quickly, but a lot of the technologies designed to usher in this next generation of nuclear is going to need to be supported by new thinking in instrumentation, modeling and simulation, training, workforce development, cybersecurity, component array reliability, that kind of thing. We're looking at new ways to use different kinds of sensors. So here we've got like fiber optic sensors mentioned. Those potentially have a lot of value for nuclear, some issues with radiation drift that we're working on. got boron coated straw, so different silicon carbide semiconductors. Modeling simulations a big part of it. These reactors are expensive to build. The more we can model and simulate, the physics, the better. The quicker we can do that. There's a lot of value here for AI and machine learning. The component array reliability piece is about, how can we treat the sum of the parts as greater than the individual pieces. So things like online training, online maintenance are quite useful. And then a word that is increasingly coming up in nuclear cybersecurity. Right now, most of the plants are analog. We don't worry too much about cybersecurity, although it's taken quite seriously. But the technology transfer for digital technologies is happening. It's going to be increasing. So we're developing some cybersecurity research apparatuses as well. One of them we call InSight, the Illinois Nuclear Cyber Range for Testing and Education. We already have a nuclear reactor simulator on campus. We're working on building a network visualization piece with some of our cybersecurity partners, where we can model networks of a nuclear power plant and then understand, how cyber intrusions would work. This also has dual purpose for training potential operators and potential workers on, what a nuclear power plant would look like, what procedures you have to follow to operate with them. And finally, a project we're working on with INL through an LDRD, we're pretty excited about. We're working with Purdue, which is a small research reactor in a neighboring state that is, cyber enabled. We're working with INL to develop some control algorithms, and we are actually very nearly remote controlling this reactor, kind of to a limited extent. And then, doing some data center simulations and understanding the power quality as we look at a really finely grained microgrid for a nuclear power data center. And that's all I got. Invite you to check out our website to learn more. Please reach out with any questions. Went over a lot of things really quickly. Happy to go into more detail later. And then with that, I'll turn the floor over.
Thanks, Tim. Very interesting. And we have a couple of questions here, but I just want to get a clarification if I heard you correctly again. You said remote control for these reactors is something which is considered?
For this project that we're doing with INL and Purdue. So Purdue is a research reactor. It's about 12 kilowatts. So it'd be a kind of a big microwave. So it's a low power reactor. They do have an experiment where you can change the reactivity of the control. So it's not a control rod that's remote controlled, but they do have an auxiliary rod where you can change the power level within tight constraints. And that we're accessing remotely. That's actually already available. We're using that capability to understand, like the power quality issues if you're going to look at a microgrid.
Okay. Now, the reason why I pick it up is, do you foresee that this would be a commercial product that you could control these reactors remotely?
So this is a topic of consideration. I would call this far term.
Okay.
People do mention remote control to the NRC, but they always do it kind of half joking and hushed tones. The NRC is receptive to this idea, but it's always, we need data. And this is actually part of why we're doing our project, with a research reactor. How do you get data on cybersecurity? And so we're looking at kind of duplicating instrumentation apparatuses so we can get this network virtualization part is a way of kind of taking steps to that over the next 5, 10, 20, 30 years, however long it takes to get there.
Okay, thank you. I have a question here from the audience for you. Please address the state of low energy nuclear reaction, LENR technology. Disclosure, I have affiliation with a company pursuing this with hydrogen as input and has done this 1,000 greater than lab scale runnings, achieving up to 2.7x net energy. So, I mean, it doesn't mean anything for me. So maybe you can speak to this low energy nuclear reaction technology.
Yeah, I'm not familiar with this technology. I'd love to learn more about it. Sounds very exciting. Yeah, please reach out. I'd be happy to learn more about that.
Okay, so Dick, I think this is something to follow up with Tim. Another question here is, what's the ramp rate constraint of the micronuclear power plant?
The ramp rate constraint. So we haven't gotten to that the stage yet. We are with the construction permit application. We're focusing more on structures and the overall safety basis. The specific operational philosophy will come with the operating license. That said, we're looking at being able to change power from 100% to potentially as low as 25%. And this will be over over hours or days going to that power. So it'll still be a slow power slow power level change compared to something like natural gas. The real enabler of the flexible operation will be the molten salt energy storage. So we're going to have a few hours of energy storage in the molten salt, and then that will let us change power as quick as anything else. And so that's why we see that value of storage that I talked about earlier, is then without having to have completely different technologies that can change power very quickly, you can still get the benefits of nuclear with sizing to the average instead of the peak power.
So another question here is, how much waste does such an SMR actually generate? Because I remember a conversation we had at some point discussing the environmental impact. And I mean, how much are you really creating here in terms of waste that needs to be somehow stored or so?
Yeah, so yeah, I don't know if I have the specific figures for hours, but I'll kind of put it in wider constraints. So nuclear produces much less waste by volume than any other energy source. So if you could take all of the nuclear waste of that's ever been used in the commercial power plant in US, which is again about 20% of the electricity that we have now since the 50s, 60s. If you put all that in one space, it would fit inside of like a large Walmart. Now, you wouldn't do that, but you can fit the waste is very low in volume. The nice thing about the HTGRs is the waste is actually very easy to store. With the TRISO fuel and with the compacts that we have, it's already in its disposition form. So when the reactor's done, you take it out, put it in a cask. Because we're a research reactor, fortunately, the Department of Energy will take it away, as they do with the other operating research reactors now. In a commercial setting, there's a lot of different approaches. Folks are looking at, ISFACs, which are, independent storage facilities, that kind of thing. From a technical point of view, not too much of a challenge, though.
Okay, thank you. And the final question, is it safe to say that we're still about 4 to 5 years out before we can realize mass production of SMRs? Question from the audience.
Yeah, I think that's a good question. Yeah, that's probably good. I think, and some things could accelerate that, some things could delay that. There has been a huge new push in nuclear that is exercising the supply chain. So, there's several new reactors that have gone critical. One new reactor actually just went critical this week, which is pretty exciting. There's a lot of things happening at Idaho National Lab, which I'm sure we'll hear about, where new reactors are coming online. And so this is accelerating the supply chain and kind of solving that chicken and egg problem a little bit. So I could potentially see it going faster than that. But yeah, we're probably more than a year or two away from kind of commercial availability of mass manufactured reactors. But I would be happy to be wrong about that.
Okay. Thanks, Tim. So with this, we close your presentation. Thank you, Tim. And we will have a second one around small modular reactors. It's from Bikash Poudel. He's a researcher in the Power and Energy Systems Department at Idaho National Laboratory. He has expertise in small nuclear reactors, integrated energy systems, and microgrids. He joined the INL in 2021, and he has contributed to several projects funded by the US Department of Energy, including work on nuclear integrated system digital twins, nuclear hydrogen production, microgrid solutions for coastal and wildfire resilient communities, and infrastructure modernization. His technical expertise encompasses dynamic process modeling, control system design, transient simulation, hardware-in-the-loop tests, load flow and contingency analysis, optimization and resilience analysis. Dr. Poudel holds a PhD in electrical engineering from the University of Saskatchewan and a bachelor's degree in electrical engineering from the University of Nepal. Thanks for taking the time, also for you, Bikash, and the floor is yours.
Yeah, thanks, Michael. Am I audible? I guess so. Yeah.
Yeah. We can see your slides, and you're coming through fine.
Cool. Yeah. Good morning, everyone. Thank you, Michael, for the introduction. So I'm a researcher at Idaho National Lab, and the topic of my presentation is nuclear power microgrids, which is one of the key research area at Idaho National Lab. I'll primarily be focusing on the research and testing capabilities we have at the lab and share some of our research we have done in recent years. So yeah, Michael has already introduced me, so I'll kind of move on to the next slide. So here, I just wanted to give a brief overview of what INL is to the folks who haven't had a chance to visit us or learn about us. So INL is one of the research laboratory owned by the Department of Energy. We are mostly focused on nuclear research, but anything related to energy innovation is an area of interest to Idaho National Lab. So at INL, the research happens in two isolated but highly interdependent research environments. So we have first research environment called Research and Education Campus located in Idaho Falls, where majority of concept development, prototyping, and lab scale testing happens. And once those technologies are ready to be field demonstrated, they are taken out at INL site, which is a large facility that we have at the lab located 28 miles west of our Idaho Falls campus, where different testing facilities are scattered throughout. So we do full-scale testing of the new concept we develop at the site. One cool thing about INL site is we own and operate our own mini grid, which is 144 miles of high voltage transmission and distribution lines with 10 different substations. The substations essentially feed to different facilities scattered at the INL site. We have been developing, testing, and demonstrating multiple reactors over the past, and we currently have 4 operating reactors. And in fact, there was one commercial reactor, commercial prototype that went critical last week, and there are many more that will be demonstrated commercially at a prototyping scale this year. So, as I mentioned, we own and operate our one mini grid, which is the 138 kilovolt transmission load that basically connects different facilities across INL. And one of the key facility at INL is Critical Infrastructure Test Range Complex, or CITRIC facility, which is an important facility to do majority of electrical testing. We bring in new electrical components, new generators, new assets to basically do power integration testing at Citric facility. So this is kind of the zoomed view of Citric facility. We have our own dedicated R&D substation with which this facility can be isolated from rest of the INL grid, and in fact the entire INL grid can be islanded from the external utility to do some large scale testing. We have done various transmission and distribution testing over the years, including testing different voltage classes of transformer, bringing in various mobile generators such as solar PV trailer, upraised wind turbines, as well as we plan to bring and test mobile microreactors in future. So now coming back to our research and education campus, which is located in Idaho Falls, this is one of the unique facility we have at the lab, where we have very diverse capabilities co-located in a single lab space. We have power grid emulation and real-time simulation capability in one of the corners. We have distributed energy and microgrid corner, which essentially controls the microgrid system that is located just outside this building. In the middle, we have thermal and hydrogen system. We have in thermal system, we have magnet, which is non-nuclear emulator of microreactor, essentially with electrically heated core. We have thermal energy delivery system, which is essentially connected with our high temperature electrolysis system. And then we have other assets, including battery testing, wireless charging, and fast charging on the left side of this picture, as you can see. So really like very diverse capabilities located in single lab space, which can be integrated in various combinations to virtually represent any integrated energy system or microgrid system out there. So very complementary and unique capability as compared to the site facility we have at the lab. A little bit more about another capability we have at the lab, the rapid microgrid in a box, which is located just outside the system integration lab that I showed in last slide. It is essentially a portable medium to high energy density grid storage which is designed to serve various power and resiliency functions, including seamless integration of novel resources such as nuclear microreactors and hydrogen fuel cells. We have been developing, testing, and patenting various control modes over the years, including online group adjustment for fast frequency watt, volt bar, and state of charge balancing when you have multiple of these containerized module operating in parallel. We have transported and used this asset to demonstrate black start of small hydropower plant in collaboration with one of the local utilities in Idaho, which we did a field demonstration back in July 2023. And we are also using this asset to demonstrate some of the microgrid integration aspects or test microgrid integration aspects with like our HPC, modularized HPC system, which essentially represents a scaled down version of data center, as well as working towards demonstrating the integration of upcoming nuclear technologies at the lab. So yeah, just wanted to summarize the kind of microgrid research activities we do at the lab. The first bin is the microgrid control development, where we basically build new control concepts for microgrids to support variety of microgrid missions, which could include integration of novel generation assets or support certain resiliency functions. The second bin is demonstrating system, for instance, demonstrating first of a kind nuclear power microgrid with extensive simulation and hardware in loop testing facility we have at the lab. So essentially to reduce risk for full scale development and future deployments. And basically using the lesson learned from the first events, we also develop toolkits by collaborating with companies like Xendee to produce tools that can be used by private sector, industries, or utilities to basically replicate what we do at the lab, but more on commercial scale. So really trying to summarize what we try to do at National Lab in this microgrid space. So with that, I'd like to move on to my main content of the presentation, which is nuclear powered microgrids. Tim has already provided a bit of background on nuclear and how it fits in microgrid. So I won't go into that detail. So this is kind of trying to summarize different stages of research activities, particularly focused on nuclear in microgrids. So this is how we divide the overall nuclear in microgrid research at INL. The first stage is competitiveness and readiness evaluation, basically trying to understand the requirement of application with the capabilities of technologies we have. We have more than 100 different microreactor technologies out there. So at this stage, we try to understand where the match is and what are the most suitable technologies for a given application. And on the second stage, we do pre-deployment analysis exercise, basically try to understand a different operational and control risk, anything related to modeling the system, to control evaluation, operation evaluation, and understanding all the risk associated with normal and abnormal operation is kind of is analyzed in the second stage. The third one is real-time simulation and hardware in loop test, basically to understand the functionality of equipment and basically transitioning from model to to understand the integration of equipment prior to doing full scale demonstration, which we do with nuclear technology that is upcoming at the lab. So I'll try to touch in each of these activities in my next few slides. So first thing first, we realized we don't really have a good SMR model in a microgrid analysis tool. So in 2023, we started our collaboration with Xendee to build the SMR model. We delivered the SMR model in GIS mode in 2023. And since then, we have been working on two different directions. One is functionality expansion, where we try to understand the use cases of SMR. For instance, extracting heat for variety of heat use in addition to electricity, which enables microgrid planners to model the system for commercial and industrial heat applications that will enable planners to think beyond electricity. And then the second area is database or catalog development, where we basically engage with different nuclear technology vendors to basically build techno-economic models from raw design data, such that we have those representation in tools like Xendee that will enable microgrid planners to basically select among different SMR technologies out there to support their applications. So this is one of the example case study we did exploring the prospect of nuclear-based microgrid for data center. So this slide is mostly focused on economics, where we compare different energy supply scenarios for a data center demand, which is essentially the demand profile of like our the SPC facility that we have at the lab. So we consider multiple different energy scenarios, anywhere from grid, the data center fully supported by grid, to battery and solar with grid, battery and solar in an island, and then bringing SMR in the mix with battery and solar with grid in an island. And final two scenarios are just SMR with grid and SMR and battery energy storage in an island. You can find more details about this analysis in the paper I have shown in the slide. But essentially, the key conclusion was, as expected, the battery and solar-based system will have better economic performance when there is grid to support all the deficiency with this kind of system. But if they have to support the entire system in an island, they will face all sort of problem. And as you can see, the levelized cost of electricity skyrockets from 13 cents per kilowatt hour to 70 cents per kilowatt hour. At the same time, SMR-based system will appear a bit more expensive when there is grid as compared to other grid-connected scenarios. But if the same system has to support the microgrid in an island, or in other words, be energy independent, it will have the best economic performance. As you can see, the difference between SMR in grid-connected mode versus SMR in an island is really marginal in terms of levelized cost of electricity. So just showing where SMR-based microgrid system will have the strong use case. We also look into operation here. We consider the case where we had SMR battery energy storage and solar PV supporting the data center microgrid in an island. And we consider the worst 2-week period in terms of demand variation out of the 8760 operation points that we analyzed. And here, obviously with this kind of large demand changes, all the resources you have in the system will have to respond. And the reason is there is a large dip, and the loss of load is sustained for a 2-week period. And as a result, all the resources will respond. Battery energy storage will respond by discharging and charging to basically support the transition of assets. And at the same time, the solar PVs are seen curtailing more generation during this period. And at the same time, SMR also responded by closely following the shape of the load over the 2-week period. As we looked in more detail into how SMR operated during this period, we saw SMR transition from set point to set point in blocks, basically meeting the operational constraint we set in terms of ramp rate limits, minimum power level, and minimum hold time. And battery energy storage was crucial to help SMR transition during this period. As you can see, the battery energy storage charges and discharges between successive ESMR transition from one set point to another set point. So really showing how different systems or different assets interact when they have to support microgrid system in an island. So now, like the major topic for us for this year. So this is what we have been focused for this year. We want to demonstrate the first of a kind nuclear power microgrid for data center. We have been our plan is to use different assets we have at the lab. The magnet, which is essentially a non-nuclear electrically heated thermal emulator of microreactors, basically mimicking the behavior of or thermal generation behavior of microreactor. Marvel is an upcoming microreactor that is set to go critical by the end of this calendar year at INL, which is designed to do some of this microgrid testing. The microreactor automatic control system is the control hardware that will be used for both Marble and Magnet. And microgrid in a box, as I mentioned earlier, is crucial for microgrid integration testing of these different technologies. So our plan is to demonstrate the non-nuclear microgrid using magnet in 2026 to 2027 timeframe, for which we are going to do hardware loop test followed by full integrated physical test. And then in 2027 to 2028 timeframe, we'll do full nuclear microgrid test with Marble once it is available at the site. As I mentioned, we are dealing with very expensive first-of-a-kind equipment, which took us years to build, so we don't want to put them at a significant testing and operation risk. So the approach we take is basically buying down disk with successive validation, starting from models to grid emulation to the complete physical system. So we start everything in simulation space, preferably in real-time digital simulator. We validate all the operation and controls, understand different control risks that comes with this kind of system. At this stage, all the components, including nuclear generators, microgrids, and demand, all are embedded and simulated in real-time digital simulator. And once we know the system is functioning properly, we bring in the control hardware, which is microreactor automatic control system, to do control hardware in loop test, basically to understand and make sure that control system or the simulator system can interact with physical control system. And once we know the system is working, we gradually bring in power component through grid emulator. We first bring our microgrid in a box system, which is essentially representing the microgrid in this life scale testing. And then it will be followed by the nuclear representation with magnet, and then finally with physical application. Here, this is a data center, a modularized HPC system, uh, essentially representing data center for our test. And at this stage, we have all the components in physical space, and RTDS is just acting as a hub. So once we know the system is functioning properly, we can just drop the simulated component and do the full physical test with non-nuclear representation of reactor. And once Marble is available, we will just replace magnet with Marble to do full nuclear test. And
Bikash, there's maybe a question which we want to clarify now. Just a minute ago, there's a question about the maintenance downtime. So someone missed maybe how your research is taking into account the SMR microreactor maintenance downtime as a use case. So maybe you want to speak to this more if you can, especially when resiliency is key.
Can you clarify
how is your research taking into account SMR microreactor maintenance downtime as a use case, especially when resiliency is key? So I think the question is, and I think this was somehow missed, is how you deal when with downtimes and how you keep resiliency of the system, right? Is there redundancy in the system? I think that's also what's asked here, if you have some redundant systems.
Yeah, absolutely. I think that should be considered. So far, like in the kind of studies I've shown, we haven't considered the downtime like for maintenance, but definitely that is something we have to consider like for the full study. For instance, you could have like multi-module system where you can schedule downtime of different modules, which is more practical scenario in real microgrids. But definitely, I mean, that is something we have to consider, like in our studies, I think.
Yeah. And I think, Bikash, if I remember correctly, the work that we did together, we considered this through our simulation with redundancy. So we can consider this in our techno-economic modeling if this is also the question on this. But okay, sorry for interrupting you, but it just popped up. So maybe.
Yep. Yeah. No, thanks, Michael. And I think I'm pretty much done with my presentation here. It is essentially showing the same thing. I just kept it as a backup in case I'm not able to go through that that animated version. So essentially, we start with everything in simulation space, followed by bringing in control hardware to do control hardware in loop test, and then followed by bringing in power component to do power hardware in loop test, bringing in non-nuclear representation of nuclear microreactor, bringing in physical application, and replacing finally replacing the non-nuclear representation with actual nuclear microreactor. And with that, I'll like to conclude this presentation and would be happy to take any question you may have.
Thank you, Bikash. So there are a couple of questions here. So the first one is there any specific battery technology that you're considering here for this ramping, or can any battery do this? I mean, you were talking about this microgrid in the box and the battery. So any specific technology? And I just asked also because we had battery sessions early on, so that's maybe also interesting.
Yeah, I think I mean it really depends on application, I think, and for this particular test we are going with lithium-ion battery system that we have at the lab, but it can depend on the particular microgrid application that you are building the system for. I think this particular use case is about building or forming grid with the battery-based microgrid system, and then SMR or microreactor basically representing or like providing the base load or like providing the core energy that is necessary for microgrid system. So any fast acting battery energy storage, depending on the requirements on microgrid side, would be suitable. We haven't gone into we haven't, I mean, taken deep dive into like what kind of battery energy storage will be strongly applicable where, but that is definitely something dependent on our application.
Okay. So another question, do you agree with this optimistic timeline that we will see SMRs that quickly as Tim was saying, or you think it might take a little bit longer?
I mean, I think Tim touched on that a little bit. It really depends. I mean, I felt, I mean, last year, like when, I mean, it took us years to get up to the point where we were last year, but this year, like there are many more commercial reactors that will go critical. And in fact, there is kind of one reactor that went critical last year. So really commercial, many kind of commercial vendors are actually demonstrating the technologies at the lab. So I'm pretty optimistic in terms of like the timeline. We are definitely accelerating. I can feel we are more accelerating than last year. I don't know, like if we are going to meet specific timelines, because like there are kind of many kind of different timelines that have been talked. But yeah, I mean, it definitely looks very promising in recent years.
Okay. Is another question, is there a commercialization partner at Idaho National Lab to bring this to the market, or is this just pure research that you guys are doing?
We do mostly research, but there are many. So what we are building at the lab, I mean, we already had like nuclear capabilities, like nuclear test beds where commercial reactors could come in and do the testing. There are many commercial parties that are kind of building their prototype and doing the test here. And we are building something called Energy Technology Proving Ground, where various industries, be it on the thermal application side or microreactor side, can come in and do the testing. So we don't build technology to commercialize ourselves, but we provide all the resources that is necessary to support industry grow in this space.
Okay, so I think I want to conclude with this last question, this very interesting session. I want to thank you and Tim for presenting your views on this. I again want to present all the attendees who are listening to this. Again, you need to get off this link, and if you want to join the next sessions, then you'll need to use that link. We have a 15-minute break, but then we have a couple of really interesting panel sessions coming up at 10 a.m. Pacific time or 1900 in Europe, which is about data centers. And then after that, we have a resiliency discussion panel moderated by Elisa Wood from Energy Changemakers. So I hope this was interesting, and see you in 15 minutes. Thank you.